So today we have the penultimate talk. One more talk left, actually more next week. This week is Michael Knap from Munich visiting us. The collaborator of mine, so I know a little bit. I think James knows him as well from back in time. So Michael is a condensed matter theorist, and he has been thinking about many body interacting systems, in particular 4 atom systems. But recently, he has been also looking at.
So that mic's off.
That's much off. And you're listening to the
That back.
It's being in person.
It didn't get to the awards yet. Those who would have
Like the other day, Natalie was giving a talk and question on my question. Ignore. And it's fine. It's not lying.
Everybody heard it, but ignored it.
No, I asked the question, Zoom collapsed, basically.
Oh. That should be science.
Sorry for that. Oops, yeah, the Zoom collapsed. The Wi-Fi. Okay, where are we? So, okay, what I wanted to say is that Michael actually has 2 talks because he works on many interesting different fields. Today is a JQI talk. Tomorrow will be a Quicks talk. So you will see more Quicksy side of him. Today is more physicsy side of him. That speaks to the broad topics that he's working on. I'm very happy that he could spend 2 days, and thank you very much. You can take it from there.
Yeah, thanks a lot, Mohammed, for the kind introduction and also for inviting me to here. It's really a great pleasure. So yeah, today I'd like to present to you some of our ideas which we had on investigating and probing actually strongly correlated state in Moiré heterostructures. And well, this work has been pushed by my PhD students, Fabian, Clemens, and Wilhelm. Clemens, in fact, has graduated last year. He's now a postdoc with Ashwin at Hubbard since a couple of months. And then we also benefited a lot from collaborations and discussions with Mohammed from here, and also with Atach from ETH Zurich. So, we want to explore strongly correlated states, and there is a really a broad number of settings where we can do so. So this ranges maybe from solids to up to quantum computers, where in this arrow I want to show somehow the level of control which one has on those systems. Today we are going to focus on something which is more here on the left-hand side, which are 2D materials. So why do I find those settings very exciting? Well, on the one hand, 2D materials have tunable carrier densities. So we have tunability in these systems. We can adjust how many electrons or other type of particles maybe I do have in these systems. We can reach very low temperatures and strong interactions, in particular compared to cold atom settings, where basically the limiting factor often is the relative temperatures which you can reach in these settings. And what I'm very excited about actually is that we have new probes which are available to poke and to investigate these strongly correlated states. And this talk will be focusing a lot on how we can kind of poke and probe strongly correlated states. And by the way, interrupt me anytime, of course, as usual. If you have questions, also on Zoom, just speak out. And I'm happy we can have this very informal, I think, and have some discussions if you like. Good. So the setting, the 2D material which I'm going to focus on today are transition metal dichalcogenides, TMDs. So these materials have a honeycomb structure, but in contrast to graphene, they have an broken inversion symmetry. So the band structure is still dominated by the K and K prime points, but it's not linear, it's gapped. These are direct band gap semiconductors, and basically you can think about them a bit like this. So we have parabolic band structures dominated from K and K prime valley. And in particular, there's also a so-called spin momentum locking. So as you can see here, the spin of the band is fixed in these materials to a specific value. It depends now what kind of system you're looking at, whether K value is maybe the valence band is up, spin up, or the other way around. Okay, but this is known. And very importantly, you can kind of layer this material and build heterostructures out of them. So you can basically have multiple DMDs and you can gate them and have a lot of control over the properties in this system. Okay, so when we want to think about these direct band gap materials, then in the standard situation, they actually charge neutral. So we have here a valence band, conduction band, and that would be the band gap. So the cartoon picture, how we want to think about these systems is illustrated here. Then we can gate them and dope in charges. Here the conduction bands will be filled by a certain density of electrons. And we can also do it in the opposite way. Maybe we can pull the chemical potential down and dope in holes. But what is very interesting, because these are direct band gap materials, they also allow for optical excitation and the formation of excitons. So these are bound states of electrons and holes. And in these systems, it turns out that the binding energy is ginormous. It's about half of an electron volt, which is much larger than all the other scales which we typically consider in this system. So Fermi energy is maybe on the order of tens of milli-electron volts, and temperatures, of course, are much lower, right? Because room temperature, as you know, is 25 milli-electron volts. So these particles here are usually, we think about them as tightly bound objects, which we can often treat as bosons. So we can replace these excitons, you see here these particle hole bound states, as a single blob, which are these bosonic particles. And there's also another feature which we have. So there can be a bound state between an exciton and an additional charge, which in the context of semiconductors usually is referred to trions. And this just comes from the fact it's a three-body bound state. You can think about it in that way. We have two electrons, maybe opposite spins, and they form a bound state with an additional hole. Okay, it's a charged object. The trion is a charged object. The charge is a charged object. The exciton is a charged neutral object. So you see, this setup is in many aspects relatively similar to cold atoms, actually. So we have different types of particles with different statistics, bosons and fermions, which are interacting with each other, and there's a lot of tunability going on. So when we want to model what is happening in the system, as I told you before, we basically have these dispersions at the K and the K prime valley. So the free dispersions of the particles we can just approximate by a parabolic band. So basically here, this would be the dispersion of the charges. And then we have a dispersion of the excitons, which have a different mass, of course, because this is a two-particle bound state. And then they interact with each other, actually effectively with contact interactions. That has to be worked out because we have a charged object and we have to do multipolar expansion. When you have, now it depends a bit on the situation which you're looking at. At the moment, I'm still talking about a single layer. When you have an exciton there, and a charge, then the effective interactions would be 1 over r to the 4 when you do a multipolar expansion. But it turns out that in 2 dimensions, one can show that this is effectively a contact interaction in the system. So now, when we think about this effective Hamiltonian, what do we have? So now we have a Fermi sea of electrons. We have impurities immersed into this, we have excitons immersed into this Fermi sea, and they are interacting with respect to each other with some contact interactions. Now we can take the impurity limit of the excitons. So just create very few of them. Use a gentle laser to maybe optically excite only a few of these excitons. Then we have a problem which we see often in cold atom settings, actually. We have a bosonic impurity. The statistics anyway doesn't matter because we're considering the impurity limit, which is immersed into a Fermi sea, interacting with contact interactions. And that's the canonical example, well-studied example of a Fermi polaron. Because we have a Fermi sea, which is dressing basically our impurity particle, we get a new quasi-particle, which is this so-called Fermi polaron. And there it turns out that we can have 2 different types. One of them is the so-called repulsive polaron, where actually the impurity, I mean, cartoonish way, pushes out electrons away from it. It's a metastable state, a high energy state. And then there is an attractive polaron where the electrons actually sucked in to the impurity. Okay, so these two situations we have, and we can literally think about the many-body state as something like a Fermi C and an exciton, or plus a Fermi C and an exciton and particle hole excitations. So this is a trial wave function which approximately describe what is going on in these systems. And when you solve this consistently and solve for the spectrum, indeed you find a repulsive metastable polaron and an attractive polaron. And on the right-hand side, I show you some experiments from Adach's group, Adachi Momoglow's group from ETH Zurich, where they actually now tune the gate voltage. And when you go down here, and we can focus actually on the upper part here of this plot for illustrative purposes, we start in doping charge carriers. So this is what you can see here, the bare exciton line shape. So this is just nothing is happening here for a little bit of gate voltage, but then up at this point, a kind of shift occurs to lower wavelengths, so higher energies, which is this formation of the repulsive polaron. On the other hand, we see here an attractive polaron formation, also a new resonance occurring as soon as we have charge carriers in the system. Okay, so that's what we have here. So far, well, actually, it turns out, since relating a bit to the cold atoms community here, so we have also worked out that you can have a tunable interactions between the excitons and the electrons, the charge carriers. Usually this is very hard. When you're solid, you realize your system and you have some intrinsic properties of your material which determine basically the effective interactions. But here it turns out we can realize a situation. It's a bit more complicated than what I explained to you here. You can realize a situation though where you have an effective description of a Feshbach resonance between the charge carriers and the excitons here, which leads to a hybridization essentially and tunable interactions. And the interactions are tunable effectively by the application of an electric field perpendicular to the sample. In these settings, however, you do have to have a bilayer situation so that you can bring bound states in resonance and effectively enhance interactions. I don't go much into details here, but what's nice is that we have this tunability of effective interactions between bosons and charge carriers also in the solid state context. So there's a lot of control which we have in these kind of systems. Okay, what I want to focus more on today is actually want to keep this polaron or dressing of the exciton picture in my mind. And however, I want to study now exotic states, so strongly correlated states of matter. So far, I've just looked at the Fermi liquid. You know, I've basically assumed that I have a Fermi sea of charge carriers. I immersed my exciton into it, and I explained to you how the dressing in the polaron formation works. But now it turns out what's very exciting about these systems is that we can realize vast classes of strongly correlated states. For instance, we can have correlated insulators or generalized Wigner crystals on lattices. We can have excitonic insulators in these systems, like dipolar excitonic insulators, or we can have quantum Hall physics at large. I mean, very different cases of with magnetic field or even anomalous cases. And the question is a bit whether we can use these optical excitations as a probe for these strongly correlated states. And what can we learn from that? That's a program which we have been pushing over the last couple of years, and also which has been pushed here by Mohamed's group in the last couple of years to understand what can be done using the optical exciton as a sensor for these exotic states, if you want. And I'll show you a couple of examples in this talk. So that's the idea. Okay. So the first example, I'll still focus on something, well, semi-exotic, let's put it like this. I will show you how we can write down microscopic models for interlayer excitons actually as a probe of some states in Moiré lattices. So these states are again either Fermi Cs or generalized Wigner crystals. And then later we will see how to stabilize and probe quite exotic quantum many-body states of matter, which are so-called chiral spin liquids in these settings, and and study a bit their robustness. So that's the plan for today. Okay, so now there's the highly anticipated twistronics picture, right? So we want to see Moiré going on. So we assume now a heterobilayer for the beginning. We have H stacking, which means that I take one layer of TMT material, take another one which is 60-degree rotated, comes now. So this is like why the blue and the red dots are not on top of each other. And now I do my keynote twistronics and create a Moiré pattern essentially by kind of rotating them by an angle of here, it's on the order of, I think 7 degrees or something like this. And then you see that there is a triangular lattice popping up here on top when you squint your eyes, which is basically this effective description which is going on. So it turns out that what we will have here is we have effectively a triangular lattice system. We have strong interactions, and it turns out very nicely that one has now excitons which are a bit more complicated than the ones which I showed you before. These excitons are now interlayer excitons, so they are bound states between the two layers of these two systems. Here we have a heterobilayer, and in particular focus on the example of tungsten diselenide and tungsten disulfide, for which the experiments here in Mohammed's group have been performed. And you know, when you now take this system, and I'd like to, I guess many of you know these results already, but let me recap a little bit. So what we want to understand now is actually what are the properties of this interlayer exciton. And so in the experiment, Pranshu and Daniel, with theory support from Chung Chang, they have investigated the photoluminescence of this bilayer system. And it turns out, you know, now translating back to what I have shown you before, so here, in a function of the y-axis, we are actually increasing the doping in the top layer. So here, basically, we start out with charge neutrality. This is the normal exciton line shape. Then, at a certain gate voltage, we start to dope the sample, and there the system shifts to here to lower energies, and this is the formation of the attractive polaron, we believe. So this basically, what's happening here is that we start to dope extra charge carriers, and then an attractive polaron is kind of forming, and the energy is shifted, or the energy of this resonance is shifted to lower energies. Then there's a little bit of squiggling going on, and when we increase the gate voltage a bit more, all of a sudden there's a large jump in the spectrum, which now indicates that we have filled the top layer with 1 electron per site, and we have to now, for the next electron to put in for further doping, we have to pay an interaction energy, which is the mod interaction energy. So that's the mod gap, which results in here for this specific material into a blue shift. In which direction this goes, this depends very much on here a bit on the microscope, on the sample which we are considering. In between, I was saying that there's some squiggling going on. So this is indeed structure which is important, and it's an indication of the formation of some Wigner crystals on lattices. These we call often generalized Wigner crystals or correlated insulators. For instance, think of the triangular lattice where on the 3 sides I remove 1 particle, then I would have like a honeycomb lattice which is left, and this would be a stable crystal which is stabilized by the longer range interactions in the system, and this will give rise to some this will give rise to some squiggly here in this response of the system. So this sample is particularly nice because we have large mod gaps and small inhomogeneous broadenings, so the lines are very sharp in the response. Yes, go ahead.
I just missed the definition of Moiré heterostructure, and also what is the experimental signature for that. So is it possible to mimic the signature by something else?
So Moiré heterostructure just means Moiré means that I do basically that I form a lattice with a larger length scale by putting, well, first we have 2 layers of my semiconductor. They have an intrinsic lattice scale of some A0 if you want. When I put 2 materials on top of each other and twist them a little bit, then there will be a super lattice forming with a much larger length scale, and this is the so-called Moiré lattice. And the effective description, I will go more into the detailed modeling later in the systems, but the effective description is then that I have a triangular lattice system with a relatively large unit cell at my disposal. So that's what where the Moiré physics is coming from. As a consequence of this large unit cell, what we have is large interaction energies compared to the kinetic energies of the system, because large lattice spacing means small momenta in the Brien zone, so there's a lot of backfolding going on, and this in turn means that, you know, the bands, they are not dispersing very much because I am going back. And this is why in these kind of settings, we have the opportunity to observe many strongly interacting states of matter, and they have been observed. Mm-hmm.
So the attractive polaron discontinuity is, I mean, is that the polaron or is it the trion formation of that? Is that the trion formation?
Right. This is also a bit the question which one needs to understand, and I think this is ongoing discussions at the moment. What is precisely happening? Because on the one hand, and this even. So first of all, maybe now I have to explain a bit more since you bring up this question. First of all, here I'm showing the photoluminescence response. It's not the spectral function which you would measure in reflectance. So photoluminescence, basically, we also don't have a good theory for PL, but how we envision it is that you basically shoot in energy, everything is drizzling down to some metastable state, and then in the end you collect the light of the decay of this metastable state. So basically this would mean that I'm going into the lowest optically active state. This is what I'm seeing in PL. And now the question is this the attractive polaron or the trion? This is very subtle. We do not know in general. So it could be that this is the trion response, but morally, at the moment, this is also something which we need to think a bit about, how to distinguish these two responses. At the moment, it's not terribly important for what is happening. The point is here, this will be a dressed object, either it's a bound state or a bit of a dressed object, which exists due to the presence of the fermions. And it turns out, even when you think about the lowest energy states and you solve the simple model systems, it depends on the parameters whether the trion is the lowest energy state or the attractive polaron is the lowest energy state. It's not, this is very subtle actually. This
The reason I was asking is because there's for the mod, I understand why there should be a discontinuity, but the polaron.
Okay, this is also, I mean, Brancho maybe can answer this in much more detail, but the point is here, what they tell me is that when you start gating the sample, there's a Schottky barrier, and you cannot dope epsilon charge carrier into the sample, but it will be a bit of a discontinuous doping, and this is why we cannot access now epsilon doping, but only some.
So the y-axis is not radiance. Okay.
It is a bit more tricky, maybe, to have the. So it's like on a coarse-grained scale, it is filling, but it's not a linear translation. It's a bit more tricky. Mm-hmm. Very good. Okay, good. But at least we see upon doping interesting new behavior of this resonance. Okay. So now what's very interesting, and this is where I want to head to, is actually, you know. So in the experiment, what they could show is they could measure essentially a length scale of exciton transport. So the idea is the following: take a laser, it's a Gaussian profile, and then collect the light. This will be a new profile. Then from the difference of the two profiles, you see how far excitons are traveling in space. In addition, so this is basically the blue line here. You see the structure going on. In particular, the length scale is gigantic near filling 1. So it goes up by an order of magnitude, roughly. And on the other hand, one can also measure lifetimes of exciton by some dynamical pulsed measurements, essentially. So this is the green curve. And you see also a lot of variations here as a function of the background of the electronic state. And now, from these two quantities, length and time scale, one can extract a diffusivity, like dividing just the length squared by time gives a mobility or diffusivity for the system. And you see gigantic variations of this quantity as a function of the filling. In particular, there's a so this is logarithmically scaled here. There's a 3 orders of magnitude increase of the diffusivity in the vicinity of the mod insulator. So the properties of the exciton are strongly influenced by the presence of these correlated states. And this is what we wanted to understand. And basically the picture this paper, what we came up with is that, well, if you have a charge neutral region, the exciton is hopping around. When we start doping, well, then actually an attractive polaron is forming, or a trion, if you want. We don't really fully know, but surely it has a different effective mass. So this means that the transport properties should change. In particular, it gets heavier. This leads to a reduction of the diffusivity, as some are seen here in the experiment. And then in the mod region, something interesting is happening, because there, the exciton now, which is forming, let's say, between this particle from the mod state and the hole here, well, actually, it doesn't know to which particle the hole is bound to. It can just basically become much more mobile by going through the system. And we called it basically a crossover from a monogamous exciton dynamics to a non-monogamous one where the charge carriers are shared. So the question is a bit, can we make this a bit more quantitative in some sense? Can we write down model systems which are able to capture some essence of this exciton formation? That's what we set out with. In particular, Fabian did the work there, and this is work together with Mohammed. There we basically, how do we approach this? Now we have to take into account all these correlated states of electrons in the back. And the exciton itself is not really point-like anymore, at least in these cartoon pictures, because the exciton can be either non-monogamous, distributed over the sample, or it can be a point-like particle. So how the heck do we deal with this? And so what we thought is, well, let's just write down an all-electronic model for the system, where we basically write down an effective Hamiltonian for electrons, for holes, interactions between electrons and holes, interactions between electrons, and solve for the exciton structure in this model. That's the strategy. We don't need to consider interactions between holes, because those are, we have the impurity limit of the hole, because we are thinking about a single impurity forming in the system, okay? So the Hamiltonian is complete when we are considering a single band description for our problem. So how do we go about? So the program consists of 3 steps. First, we need to solve for the correlated electronic state. And this may be a generalized Wigner crystal like the one which we show here, where the charges are sitting on these hexagons here, and in the middle, the sides are empty. This could be one state which we find by solving for the ground state of the system. In fact, we could do it in different ways. We just use a self-consistent mean field theory to solve for these type of states. Then we need to find what are the bound states, particle hole bound states on top of these correlated states. So what we have to solve is we solve the two-body problem of an electron, an additional electron, and an additional hole on top of the ground state. Project back to this basis and so search for whether we find a bound state in the system or not. This depends on the parameters of my model, how big the attractive interaction is, etc., which ideally we want to determine from experimental input, but we could use here in our model just as model parameters for the moment. And as a next step, we have to deal with the polaron formation. So far, I have now correlated state, exciton formation on top of it. Now I want to trace the exciton with the charge environment. How do we do it? It's literally the same as we did before, that we take exciton and correlated state, plus a superposition of exciton and particle hole excitation in the correlated state. So previously it was particle hole excitation on top of the Fermi C. Now we take particle hole excitation on top of the correlated state. This is solved self-consistently. It's a variational state which we optimize for, and then we can extract out of this the spectrum of the polaron. So here is the energy of the resonance as a function of momentum. Optically active is only the zero momentum response, because you know the energies are low here in the system, so speed of light is basically infinity. So all what we can see is zero momentum response of these spectral features here. But I just wanted to show you how this dispersion in general looks like. Well, and now we can play the games, and we can put in, yeah, go ahead.
Step 2 and step 3 calculated for the same load.
Come again?
The step 2 and step 3 calculated for the same load.
Step 2 and step 3, yeah, so first we set a state, which is an all-electronic state. Then on top, I create a particle hole excitation, which is basically a two-body problem, but not in the vacuum. The two-body problem is solved on this background structure. And then later we do it self-consistently with particle hole excitations, which is stressing the impurity. It's literally one-to-one the same program which we have for the normal polaron formation, but now with this correlated state. And this, of course, cannot be done as analytically as for a continuum Fermi C. So we need here to do these steps numerically. Yes.
What is the control parameter that determines if your variational polaron state speaks only one particle hole excitation from mixio even more?
Yeah, no, of course. So the question is whether the WISE is a good answer. That's what we are using here with one particle hole excitation. So we do know, so in Cold Atoms community for polaron investigations of Fermi Cs, this is called the Chevy ansatz. So it's basically, let's say, ground state plus one particle hole excitation. And there in this dilute limit, it is known to capture the physical properties of the system very well. And there has been a lot of benchmarking done with Monte Carlo sampling and so on. And this was basically a very good description. So here, this is the best. So we basically close our eyes and hope that it's still working in this context, because it's very hard. One would have to do a similar effort of benchmarking for these type of states as has been done in the Cold Atoms community for the normal polaron formation in the continuum. Because even there, people first thought, no, I mean, it cannot work, what this ansatz is doing. But then there has been a lot of numerical efforts and shown actually that indeed it does work. And one would need to, this is just the beginning. If you want, there's a lot of work which can be done to maybe make this more accurate in the end. But at the moment, all what I want to have is a simple toy model for describing the dressing of an exciton in top of these states. Okay, and then first now we literally redo the same exercise as before. Don't use any correlated state, but just a Fermi liquid, a Fermi C, and solve for the polaron formation now in different stacking. So there, you can have different stacking geometries in these DMDs. Either particle hole is sitting on top of each other or a little bit like in between of a triangle. You can now, with this all-electronic model, solve for this problem. And basically, we see, well, nice, there's a spectral feature here and another spectral feature here, which we attribute to repulsive and attractive polaron. And when you compare to the single layer results, this is kind of similar there. And actually, it's highly non-trivial to get this. For instance, we need to take spin-full electrons to properly describe the splitting here between repulsive and attractive polaron and so on. So it's not that this is easy in some sense that this comes out in that way. Okay, but when we do it, we see that the continuum limit, the low density limit, which is kind of shown here, this is the low density filling, indeed looks a bit similar to what we would expect for the normal polaron formation of an impurity in the Fermi C. Now we can look also at more exotic states. For instance, we can now look at the generalized Wigner crystals. For instance, here the 2/3 filling, and look at the exciton formation in this setting. Turns out it's actually quite interesting. So we are now looking only at the repulsive polaron peak. The attractive polaron peak is just not out of the picture here. But what we see is instead of a single peak, we see multiple peaks in the repulsive polaron spectrum. So where is this coming from? The idea here is the following. So assume that I have an exciton which is in a liquid state. Then the dispersion will be basically parabolic. And I see the momentum zero response of the exciton. This is my one exciton, or let's say it's also then the repulsive polaron peak in the spectral function. When I have a charged ordered state, however, then you can think about it in a way. Remember, the effective interaction is a density-density interaction between charge carriers and the exciton. When we take a mean field level, a mean field description, so mean field decouple these two states, and assume that the charge carriers are in a periodic potential, then what I have to effectively solve is that my exciton is living in this periodic potential. That means that I get a Briand zone for the exciton, and the band structure will be backfolded in this Briand zone. That's illustrated here. So the band structure is going to be backfolded, and this means at momentum zero, I get a new resonance which is appearing. Okay. It's literally a single particle QM problem. The new resonance is appearing here at finite energies. And indeed, this has also been experimentally demonstrated here a while back. There we did literally the mean field picture. So here we do not apply this decoupling of the exciton and the electron on the mean field level, but we solve this all electronic model, and we still see that there is a additional umklapp, we call it umklapp or backscattering peak, emerging at higher energies above the repulsive polaron, which comes from the backfolding of effective backfolding of the exciton dispersion. And now it turns out it's actually very interesting. Yeah, go ahead.
Could you use that as a probe for melting this probe?
Yes, in fact, actually, so we did it here in this experiment for a so-called Mott-Wigner crystal, which is basically the integer filled crystal here, and saw the umklapp peaks emerging at integer fillings. It turns out in a follow-up experiment, Ataj actually used this probe to get signatures of the formation of a Wigner crystal in a continuum system. Because a Wigner crystal transition would be a crystallization transition where you basically also spontaneously break because of binning, you spontaneously break translational symmetry in the system, and you would see these signatures. There it is less clear than what we had here in the static case, but you at least got some information about the melting of the Wigner crystal using this type of probe. So it's like a non-invasive probe of charge density wave order in these kind of systems. Now it turns out you can play these games even further because there are some spin. If you now consider the spin texture on top of these Wigner crystals, we don't know at the moment what the nature of the spin textures is in these materials. It's an open question. But if, let's say, the spin texture would be like strong and either ferromagnetic or antiferromagnetic, for instance, this umklapp peak would give you different response, because in a ferromagnet you would have C6 rotational symmetry, and you get only one umklapp peak, because all the bands are basically backfolded in the same way. For antiferromagnet, you would have only C3 rotational symmetry, and in principle, you get splitting of the umklapp peaks. And indeed, this is also what comes out of this all-electronic model. So you see a nice splitting of these umklapp peaks. So you can also use it to detect a little bit the magnetic texture in these systems. Okay. Yes. Good. Okay, and maybe most importantly, what is also happening here, there's a strong renormalization of the polaron mass as a function of doping. So for instance, here the bare polaron mass is roughly 0.5 T, whereas the polaron mass of this attractive polaron object, which we get from our solution, is a factor of 10 smaller. And this indicates already a strong renormalization of the properties. And in particular, also when we go back now, say, we would hear maybe something like 0.05 is the exciton mass. However, in the vicinity of crystals, this goes back up to a factor, I don't know, 20, 40 larger again. And you know, this is now a little bit of a indicative of the experiment which we have seen before, because there we also saw that near the Mott transition point, which is basically showing here, this would be a strong Mott state here, this data, we would get again a strong renormalization of the mass of these polarons which are immersed in this system. So that's a prediction of this all-electronic model, if you want, for this exciton formation, which tells us a little bit about the inner makings of these correlated states. But there's a lot to be done, as we have seen already. So I mean, do we understand properly attractive polaron versus trion, for instance, or for instance, we have not built in a proper Mott transition in this description. Can we find an effective description also literally in a field theory way, maybe, where we can capture Mott transitions, which is theoretically not so easy to be done, and so on and so forth. So these questions can be addressed in that way. Okay, good. But the upshot is that with this all-electronic model, we have somewhat a nice tool, I think, to capture exciton formation in more complex structures, or polaron formation in more complex structures than just a rotational invariant Fermi sea.
So, to what extent does your exciton spectral function correspond to the photoluminescence that is measured?
Yeah, so this goes back. So the question is again for Zoom people. how do we know that PL has something to do with the spectral function which we have predicted here? And again, we just can rely to these heuristics which I was arguing before, that basically in PL, we go to the lowest energy state, and then we look at the decay of this lowest energy state. And if this attractive polaron is the low energy state, then this would be the signature which we will get. And in the experiment which I was showing you from Mohammed's group, there actually we think more about actually a transport question, right? We probe how are excitons transported over in space and what is happening there. And there we can just use the information which we get from our formation of the exciton and dressing as input, because we see strong mass renormalizations, and this would be indicative then again of somehow seeing strong renormalization of the diffusivity or transport properties in the system.
But I was wondering if you can compare your, like, to the PL spectra, the theoretical results.
You mean
determined parameters?
Yeah, so there, as you see, there are many layers of uncertainties. First of all, we do not know the microscopic parameters for this system because we don't have reliable estimates. And even there's a lot of wiggle room. It is hard, I would say. I mean, but this is, of course, would be very interesting to do as next steps. So one could see, is this even quantitative or something like this? But on the other hand, you know, hoping to get something quantitative out of it is maybe a bit of a long shot, because here we do like Hartree-Fock approximations, bound states on top. So there's a lot of approximations involved, but at least we get some intuition about what is going on in the system. So you should see this more in an Occam's razor way, that we have an effective model of describing roughly what is going on in there. To have quantitative descriptions, maybe one needs to combine these techniques with some more ab initio type techniques or something like this. I don't know. I mean, this would be beyond.
The first order of business is to show that actually they exist.
Yeah, which is where we are at the moment.
And we were just arguing with the referee, that the referee says, well, there is one experiment that they're trying to publish, and it's another experiment, then it's not actually related to this.
Yeah.
And it doesn't exist. So just the presence that in an experiment and a theory it exists, it's one step.
Yeah, so we are at that level that you literally want to write down simple systems, model systems, which capture essentially this essential physics.
I guess I was motivated by the first experiment. You had this first experimental plot that was nice at showing all the various features.
Yes. Yeah, perfect. But the question is, do we? Yeah. Yeah, so in principle, yes. I mean, what I wanted to say is that, for instance, one prediction of this model is the strong mass renormalization, which we get. And this is would be then observable, for instance, in the change of the diffusivity, which has been seen experimentally. So on this very qualitative level, we are kind of trying to make comparisons at this point. Okay, yes?
Sorry, I have a question. So is there some sort of argument that one wouldn't be able to observe this with just a Fermi-Dickinson state, or like, here when you say strongly correlated?
Oh, the question is even whether this bound state is forming or not in these lattice systems, let's say of a trion or of an attractive polaron. So questions like this are actually not so easy to completely clearly positively establish. As we try to work now to understand this from different perspectives and hopefully establish this picture.
Perhaps, again, a very naive question. In your view, what would be a definitive signature of the formation of such states? Like, what if one could measure little experiment, what should one measure?
Yeah, I mean, what would be nice, of course, to have is some direct optical probes, which are difficult for these kind of indirect excitons because of energy scales which are involved, but that would be ideal. Or, I mean, to test more of our predictions, for instance, the exciton formation here, I glossed over it, but maybe I can just go back to it. Turns out that when you start filling the conduction band to a high enough value, then it turns out that the mass of the exciton will be inverted because the electrons have a negative mass. And this will have consequences, right? So the polaron dispersion will not be upward band, but downward band. And those things this is our prediction from this model. And those things you could measure in Hall type measurements, because Hall type measurements pick up the sign of the mass, essentially, of the charge carriers which you are measuring. So those things, they're little bits and pieces which we can use to kind of establish more and more this effective picture. Okay. Good. A little bit more? Do you have a bit more time? Or?
Yes.
Yeah, okay, good, good, good. So then, so point one is done. Okay, good. Do we need to? No, it's a bit less. No, we won't do too long. But the point is now, okay, we have now looked at these excitons, how they can be useful as probes of correlated states. Now I want to study a bit more exotic correlated states. In particular, I want to go into this direction of states with topological order, but in particular focus on the chiral spin liquid. So I'll tell you more what this means. The system which I want to investigate now is relatively similar to before, but it's a homobilayer situation. So we do our twistronics again, so you know the drill. So basically we get here this effective triangular lattice model. And for the homobilayer, it turns out that we literally get a single Hubbard band, essentially, where top and bottom layer act in a symmetric way. So they act as pseudo spins, if you want, of the electrons. So there are two bands which are degenerate for the top and for the bottom layer. This is because we have a homobilayer DMD system. So effectively, we get a Hubbard model of electrons hopping on a triangular lattice, which have a, let's say, dominantly an on-site interaction energy U, and the spin degrees of freedom are now top and bottom spins. We also have the electron spin degree of freedom. So this Hubbard model is actually approximately an SU4 type Hubbard model, which we have here. However, what we want to do next is we want to apply magnetic fields perpendicular to the layer, which are then driving a ferromagnetic transition in the electronic spin. So the electronic spin will be again out of the game, and we are left with an SU2 symmetric Hubbard model in the presence of a magnetic field. And that is a very interesting model. We will see step by step. So why? First, let's take the limit of weak interactions. Okay. Then when we have no magnetic field, we would have some band structure which we can fit to, I don't know, deep or like band structure prediction simply. And we get a tight binding relation, which is like this orange dashed line, which agrees well with the full band structure calculation, which is the blue line. We can now switch on a magnetic field, and then what we get is just a Hofstadter model on a triangular lattice. And it turns out for a magnetic field of pi/2, even though the system is in a triangular lattice, there's particle-hole symmetry between, I know whether you have solved this problem, it's kind of nice. Triangular lattice is normally not particle-hole symmetric, but at this flux of pi/2, particle-hole symmetry is restored in this system. So you get these two Chern bands here, with Chern number +1 and Chern number -1. The magnetic field explicitly breaks time reversal symmetry, and large magnetic flux to kind of attain these values of a flux of pi/2 are easily achievable in experiments here because the unit cell is very large. The unit cell is on the order of, let's say, 10 nanometers. Like the length scale of the lattice spacing in this triangular lattice is 10 nanometers. So we estimate on the order of 10 to 20 Tesla, we would saturate the flux. And this is achievable experimentally. So it's a very good situation. Now let's switch on interactions. So a Hubbard model on a triangular lattice in the strong interaction limit becomes a Heisenberg model by doing a Schrieffer-Wulff transformation. Turns out that the ground state is a 120-degree ordered magnet. In the presence of a magnetic field, the next to leading order term does not vanish. We still have a so-called chiral term, S dot S cross S, which literally comes from doing perturbation theory to third order around the triangle. Normally, due to time reversal symmetry, this guy and that guy are canceling each other, you get 0, but in the presence of a magnetic field, they are not canceling each other, and you get a finite spin chirality in the system. Now it turns out that unless you have ginormously large interactions, then only this term matters, but for, let's say, large, but not too large interactions, the state will be non-magnetic, it will be SU2 symmetric, and it will actually form, as I will show you, a chiral spin liquid. So first, let's put a bit the mindset, it's important. So where do we have very strong signatures, or maybe say the first signatures of a state with topological order is the fractional quantum Hall effect, where we have explicitly broken the time reversal symmetry by applying the magnetic field. For spin liquids, things are much more complicated because when I apply a strong magnetic field, usually I polarize the spins and you just get a ferromagnet. But here I polarize the electronic spin, but I still have the orbital or pseudo spin degree of freedom left, which picks up the magnetic field while retaining SU2 symmetry on the level of the model. And this is why I think this is a very good place to search for spin liquids or chiral spin liquids in particular, because we explicitly enforce the system in this direction. Okay, good. So how can we do that? We can now maybe establish this picture, what I have shown you numerically. We can write down a matrix product state as a trial wave function and perform Laughlin's argument, so a flux pumping, to test what the nature of the phases are. And it turns out at weak interactions, what we have is, I already showed to you, maybe let's go back again. The band structure is literally just a Hofstadter problem. So that's what we would call, we find a Chern number. So that would be like, if you want an integer quantum Hall state or a fractional Chern insulator, a Chern insulator here with integer fillings. And there are actually two copies of it because top and bottom layer, they are filling these bands. So there are two copies of this integer quantum Hall state. So we call it bilayer integer quantum Hall state. When we do, now we can do a basis rotation. We can take the sum of the charge of the two charges, which we call charge, and the difference of the two charges, which we call spin. So it's pseudo spin and total charge, if you want. And in Laughlin's argument, what they say is that basically you now thread a flux through a hole in your geometry, and then particles are pumped from one side to another side of the system. And this is what a standard numerical technique actually is to detect what the nature of the states are when you use like a tensor network formulation. And here we see that in bilayer integer quantum Hall, both spin and charge are pumped, which just means that they have two decoupled bilayer integer quantum Hall systems. When you crank up interactions, it turns out all of a sudden charge won't be pumped anymore, only spin will be pumped. So that is something like a mod transition, which happens at the critical point where actually the charge gap is closing and opening up again. It's a topological mod transition. Actually, we understand the nature of this transition. If you're more interested in it, I can tell you. But here, the essence is that only spin is pumped, charge is not. And that actually corresponds then to a chiral spin liquid, actually to a spin-only state, because what it means that if charge is not pumped, it's just that charge is kept out trivially. Actually, charge is out of the business, if you want. Okay, good. So, well, maybe let me jump over this so we understand basically the nature of this transition. It's quite interesting if you're interested in topological field theory, so you can write down a parton description. Actually, it turns out that what is important is that across this transition from the bilayer integer quantum Hall to chiral spin liquid, spin is completely gapped, whereas charge undergoes a transition from being gapped to gapless at the critical point to gapped again. And actually, if you do the translations of this field theory, then the chiral spin liquid corresponds to the mod state of this topological transition, and the bilayer integer quantum Hall is the superfluid, which is then Higgsed again due to the Anderson-Higgs mechanism, essentially. And this is the nature of this type of transition. And using a parton description, you can basically understand what is going on. More importantly, maybe, is that this is not only happening at the specific flux here of pi/2, but it actually comes from the fact that in third-order perturbation theory, I create this chiral term of S dot S cross S. And this has nothing to do with the precise value of the flux, but the strength of this chiral term depends on the flux, but it's always there. Yes. Oh, this is the effective action of the transition then. So how you do this is, technically, you start out with the effective Hubbard description, identify your right degrees of freedom by introducing a parton formalism of charged bosons and fermionic spinons. And then what you can do is basically the spinons, they are completely agnostic to the phase transition. They don't see the phase transition at all. They're completely out of the business. But the chargons, they are sensitive to the mod transition. And
So, A means what?
mu is the external vector potential. This is really my magnetic field perpendicular to the system. And A mu, no, there is actually here in the chiral spin liquid, there is actually a Chern-Simons term in the field theory which describes basically the semionic statistics of the spinons. I don't go into these details here, but if you want, we can discuss a bit more in here, because this is a bit more formalism. I don't introduce here everything. But if you're interested in this aspect, I'm happy to expand on it a bit more.
So, D mu is related to the kinematical field.
Yes, so we introduce partons here. This means that I have a gauge degree of freedom for the B field and for the F field. I can introduce a local gauge field, e to the I phi, e to the I minus phi, and then we can integrate out the gapped spinons, and the effective action which we have is the spin sector is basically topologically inert. So this is this Chern-Simons term with a charge 2 in front, which basically tells me this is the property of the spinons. But the bosonic, the charged part, this is basically undergoing a mod transition depending on the sign of this effective mass m. If, now I don't know what my sign convention is, but if I have, let's say, a potential like this, Mexican head type potential, then I'm in my superfluid, but there's also charge involved, so it has an Anderson-Higgs mechanism because of the gauge field which I introduced, so the spectrum is gapping out again, whereas this is the bilayer integer quantum Hall, whereas in the mod state, charge is completely out of business. And then I still have to do flux rearrangement because I have a flux which I have to redistribute by my particles, and this makes actually the excitations of the chiral spin liquids the semions. So I can give you more, but this is a bit like a bit more, a bit too much. Okay, good. Yes. So this transition is understood, and maybe just since you are interested in this, it has been worked out by Clemens in his thesis, and actually there's now also follow-up work which basically describes this in a bit more detail from half a year later. Okay, good. But now I think I should wrap up. But what is very important and why I think this setting is very nice is, the spin liquid is stabilized by the fact that we have these time reversal symmetry breaking terms, the spin chirality in the system, and that's there for any magnetic field. The magnetic field has just to be high enough to polarize the electronic spin. Otherwise, it gets even more complicated because then I have the electron spin also to treat. This I want to avoid. But then what we have, and we can numerically study, is that there is a gigantic regime of chiral spin liquid which is basically all over in the phase diagram. And for those of you who have worked with spin liquids, this is a very rare situation, because usually a spin liquid, even in a model system, is appearing in a teeny tiny point in parameter space, usually. I mean, maybe it's a bit exaggerated, but roughly it is like this. So, and here we have it in a very large region. The reason is that we explicitly break time reversal symmetry while retaining SU2 symmetry. And we can also check stability against direct ferromagnetic exchange, for instance, which is the biggest enemy for the chiral spin liquid, and it turns out that it's still okay. I can give you more details on this. But maybe to just connect back to one more thing, because I was telling you I want to probe exotic states of matter. So how do we do it now in the case of a chiral spin liquid? The nicest experiment in some sense would be to do counterflow. The idea is that you thread a current here on the top and the current in the opposite direction at the bottom. So since these are in the opposite direction, they're coupling directly to my spin degree of freedom. And therefore, if I would measure the Hall response of the system, I would get a topologically quantized response. This is in theory very nice. In practice, it's very hard because I have to avoid shortages between the top and the bottom sample, which in real life is hard usually because you have to have very clean sample situations. So what's maybe the first step, which one could do experimentally, is actually to measure the spin susceptibility. And this again can be done optically, because the excitons, the line width of the spectra of the excitons, are actually proportional to the density of electrons because of the polaron formation. And since we have now a pseudo spin degree of freedom, I can measure a set by measuring the density difference in the top and the bottom layer. So I can use the exciton to probe essentially the spin susceptibility in the system. And then I would see in a chiral spin liquid, I would see a gapped response. Whereas if I was in a 120-degree state, for instance, I would see, let's say, a magnetic response, which has gapless excitations, is the just the Goldstone bosons of this magnet. And in a metal, it would be the metallic spin response, essentially. So this could be used as a first signature to see that we have a spin gap, which would be maybe nice already to have. And then one can do add-ons with more complicated responses. Okay. And then this is not too much, but you can also in the, let's say, scattering experiments like RPES or inelastic scattering can also be done in these samples, given recent developments of so-called quantum twisting microscopes. So they can do basically tunneling spectroscopy experiments, but with momentum transfer. And in these responses, you also see very different signatures of the chiral spin liquid and the magnetic state, for instance, which tell you about the properties of the underlying phases. So there are many opportunities which we have to probe these correlated and very difficult states of matter, which do not have any local order parameters, right? So there's no local order parameter to detect topological order, but there are many ways how we can put pieces together to basically understand these, well, first of all, one has to realize that, but if they were there, to characterize and affirmatively confirm the existence of these states of matter. That's maybe just a summary of what we've been talking about.
I have so many questions and we are over time.
Yeah, so sorry for that, actually.
Someone really feels that a question has to be asked and answered. Otherwise, we go and then he's around tomorrow as well. So just thank you again.